Hi everyone. Let's talk about antiderivatives. In the first exercise, we must find functions whose derivatives are given on the right side. If you would like to try this exercise on your own, stop the video now. You can also download these notes using the link in the video description. I believe a function whose derivative is 2x is x squared. A function whose derivative is cosine of x is sine of x. A function whose derivative is secant of x tangent of x is secant of x. These functions have a name. They are called antiderivatives of these functions. In general, a function capital F is an antiderivative of a function small f on an interval if the derivative of the capital F function equals small f of x for all x in that interval. In general, we denote antiderivatives by capital letters. For example, if someone gives you a function f given by a small f, and you take the derivative, you get f prime. But if someone gives you small f and asks you, what is a function whose derivative is f? We usually denote that function by capital F. Similarly, if the function is given by g, its derivative is g prime. Its antiderivative is capital G. In the next exercise, we must find two antiderivatives for each of the following functions. If you would like to try this on your own, stop the video now. When I'm asked to find an antiderivative, I always ask myself, the derivative of what function gives me e to the power of x? I know at least one such function. I know that e to the power of x would work, because e to the power of x, when I take the derivative of that, I get e to the power of x. I can come up with a different function whose derivative is also e to the power of x. That could be f of x equals e to the power of x plus 2. The derivative of this function is again e to the power of x. Because the derivative of e to the power of x is e to the power of x, the derivative of 2 is 0. In fact, e to the power of x plus any constant would work. I could have added 5, I could have subtracted 100. Same story when it comes to g of x. What is an antiderivative of x squared? Can I come up with a function, capital G of x, whose derivative is x squared? My first idea is to use x to the third power. But I realize this is not fully correct, because when I take the derivative of this expression, 3 comes down and gives me 3x squared, which is not x squared. I get an answer that is 3 times too big. To adjust, I will say that my antiderivative is 1/3 x to the third power. Because now when I take the derivative of this function, 3 comes down and cancels with the 3 in the denominator, giving me simply x squared. I could have written this as x to the third power divided by 3. What is some other antiderivative of x squared? I could say that I could use g of x equal to x to the third power over 3 minus 7. The derivative of this function is still x squared. In fact, I could have added or subtracted any constant I wished. This is a theorem that says that if you have one antiderivative of a function f on an interval, then every other antiderivative of the same function on the same interval has the form f plus c, where c is an arbitrary constant. Note that this is exactly what happened here. I had one antiderivative, and any other antiderivative is of the form this antiderivative plus any constant. This expression f plus c is called the most general antiderivative of f. Let's see if we understand this by trying to find the most general antiderivatives of the following functions. If you would like to try this on your own, stop the video now. I believe that the most general antiderivative of 1 is x plus c. And that is because the derivative of this expression is always 1, regardless what c is. Antiderivative of c is cx plus c. Antiderivative of e to the power of x, the most general antiderivative, is e to the power of x plus c. When it comes to cosine, I ask myself, the derivative of what gives me cosine? And I believe it is sine of x plus c. In the next entry, I cannot simply write cosine of x plus c, because the derivative of cosine is negative sine. And I need to get sine when I take the derivative, which means that the most general antiderivative is negative cosine of x plus c. Because now, when I take the derivative, I rewrite the minus, and the derivative of cosine is negative sine, minus minus gives me plus sine of x. Let's take a look at the examples on the right side. Antiderivative of x, I think maybe should be something like x squared. But that will not work, because the derivative of x squared is 2x. That answer is 2 times too big. To adjust, I will divide that answer by 2, and I will say that this is x squared divided by 2 plus c. Note that now everything will work. The derivative of this expression is 2 comes down, cancels with 2 in the denominator, and I simply get x, and the derivative of c is 0. I follow the same idea here. Antiderivative of x squared is x to the third power over 3 plus c. Antiderivative of x to the third power is x to the fourth over 4 plus c. Then I get x to the fifth over 5 plus c. I always follow the same rule. If I want to find an antiderivative of x to some power, I increase that power by 1 and I divide by the same power. Let's apply this logic to x to the negative fifth power. Let's increase the power by 1, which will give me x to the negative fourth power, and I divide by that power, and I add c at the end. Let's confirm that this works. When I take the derivative of this expression, negative 4 will come down, will cancel with negative 4 in the denominator, and will change into negative 5, exactly like we wanted. What we discovered here is the power rule for antiderivatives. The most general antiderivative of an expression x to the power of p is x to the power of p plus 1 divided by p plus 1 plus c, where p can be any real number besides negative 1. Note that p cannot be negative 1, because then this answer would ask you to divide by 0, which means this rule works for any power besides negative 1. What is the antiderivative of x to the power negative 1 then? What is the most general antiderivative of x to the power negative 1, which is the same thing as 1 over x? You're probably thinking it's probably natural log of x, because the derivative of natural log of x is 1 over x. And you're almost correct. Remember, the function 1 over x is defined for all the x's besides 0, which means this function is defined for x's greater than 0 and for x's less than 0. The function ln of x is only defined for x's bigger than 0. The function ln of x looks like the following. You can only plug in x's bigger than 0 here, which means ln of x is an antiderivative of this expression on the interval from 0 to infinity. What about on the interval from negative infinity to 0? I believe a better option is ln of absolute value of x. Let me show you why. If I take the derivative, if I first assume that x is greater than 0, I look at the interval between 0 and infinity, and I take the derivative of ln of absolute value of x, for x is greater than 0, the derivative of ln of absolute value of x plus c is the same thing as the derivative of simply ln of x, because x's are bigger than 0, which means I don't need that absolute value here, and I will get the derivative of simply ln of regular x plus c. And the derivative here is 1 over x, and the derivative of c is 0. So I get 1 over x. On the interval from 0 to infinity, the derivative of this expression is exactly 1 over x. What about on the interval between negative infinity and 0? The derivative of ln of absolute value of x plus c is the same thing as the derivative of, and now because x's are negative, to rewrite this function without the absolute value sign, I will put a minus in front of x. That is the same thing as ln of minus x plus c. That's how we rewrite absolute value whenever we know that the input in the absolute value is negative. Now to take the derivative, I take the derivative here by using the chain rule. The derivative of negative x is negative 1. The derivative of ln is 1 over whatever was inside of ln, in our case, negative x. The derivative of c is simply 0. Now, minus and minus, they cancel out, and I get, again, 1 over x. Which tells you that for x is greater than 0, ln of absolute value of x plus constant is an antiderivative. For x is less than 0, ln absolute value of x plus c is an antiderivative there. Which means that the most general antiderivative of 1 over x on any interval not containing 0 is ln of absolute value of x plus c, where c is an arbitrary constant. It is possible that that c for x is greater than 0 can be different than for x is less than 0. But as long as we are dealing with an interval not containing 0, an antiderivative, or the most general antiderivative of 1 over x, has the form ln of absolute value of x plus c.